So a little bit about our presenters today, and we're going to, Marco and I are obviously presenting here. I want to introduce Marco to everyone here in the room, and we're really, again, really pleased for Marco to come visit us here from the great country of Canada. And I know he's going to probably smile a little bit after that as well, but Marco has been a long time industry veteran, both in the service engineer, servicing side, much like yourselves, and then later as his career ladder built into the medical physics end of his career where he's at today. I can speak to, again, 25 years plus in the industry in the country of Canada, and also past president of the Canadian Organization of Medical Physics, which is the equivalent to also here in the United States, as well as globally as well, the AAPM or the American Association of Physicists and Medicine as well too. So, Marco?
Thank you, Al. And I'd like to, well, anyway, thank you for allowing us to be here. And I'd like to return the favor and introduce my co-presenter, Al Moretti. Al has been in the industry a little longer than I have, so I think I can say that. And he is a strategic leader and a strategic thinker. He's been a patient advocate involved in both the radiation oncology industry as well as the HTM sector. So he has a these are two industries that are sometimes viewed differently, but Al has good knowledge of how they interconnect with each other and how they relate to each other. He's been, so 39 years, which is a little longer than me. So we'll just leave it at that. And he's also the founder and past president of the Clinical Engineering Association of Illinois and an HTM industry. And he's presented at many conferences. So thank you. Yeah. So what we're going to do is we're going to kind of go through, I'm going to go through a few slides, and then we'll talk a little bit about, as Al said, radiation oncology, linear accelerators, how this works together, and then we'll kind of go back and forth, and then I will kind of finish it off. So we have some learning objectives for today. So we'd like to, mainly what we'd like to do is just keep it simple. We'd like to introduce radiation oncology to the HTM professional. So traditionally, these industries have like with the radiotherapy center within a hospital and kind of the rest of the hospital, they're kind of separated a little bit, and so there's a bit of kind of sometimes mystery over what goes on over there, or they're not really as integrated as really they could be. So we just want to talk a little bit about what happens. It's not, there's no secrets, and what it's all about. And to discuss a little bit about the main device, which is the medical linear accelerator, the technology involved with it. So medical linear accelerators are complicated devices, and we'll talk a little bit about that. They're not that complicated, but there is a bit of a kind of a unknown factor about them. So hopefully we'll kind of reduce that. And then we'd also like to discuss some of the traditional mechanisms, the traditional methods about how these machines have been serviced, how that's why that is, and then maybe there's some opportunities for some people like yourself in the room to maybe become involved. And so this is kind of our goals. And as Al said, as we go through this, and I'll kind of get into some of the details around radiation oncology and linear accelerators. Please stop me, put your hand up if you have any questions. We have lots of time, and so hopefully, so let's make sure that we don't, there's nothing that you don't know and can ask questions when you want to. Okay. So this is the slide, the one part that's meant to scare you, but it's not that. But that's the only one that's meant to scare you. So cancer affects 1 out of 2 people in the United States and the world today. It's actually not quite that bad. It's probably somewhere between 40 and 50%. So cancer is a disease of aging people. We live in a world today where the median in our lifetimes is getting longer, which is a good thing. However, as we get older, the incidence of cancer increases with age. And so today, if you go to the American Cancer Society and you look at their statistics, and they'll give you the exact numbers, but it's close to 1 out of 2 people will be affected by cancer in their lifetime in the United States. But that means that sometime in your life, 1 out of 2 people will get a cancer diagnosis, which is, so that's the scary part. The good news is that we have lots of ways of treating cancer. A cancer diagnosis today is not what it was 20 years ago, 30 years ago. It's still a serious, serious disease, but there are many, many more options now than there were before when I started in this industry. And the main ways of treating cancer are there's surgery. Surgery is the main, usually the kind of the first approach that we try. Most people think about chemotherapy as well, and I'll talk a little bit more about all these three in a second. So the chemotherapy is, pretty, well-known, way of treating cancer. But the lesser well-known is using radiation, so radiation treatments. And radiation is a very effective treatment of cancer because it's unlike some chemotherapies, and I'll talk in a minute. It treats all cancers. And unlike surgery, you don't need like an incision. It's less invasive. There are of course side effects, but you don't need there's not an operation. And so surgery and radiation are what are called like local treatments. And so we're treating a specific area of the body. Whereas chemotherapy, we're treating the whole body. So you infuse drugs. And so as diseases advance, chemotherapy is more needed for advanced stage diseases where the disease is spread. Whereas early stage diseases, stage 1 and stage 2, surgery and radiation therapy are often kind of used. And each cancer is different. Excuse me. Each cancer is different. Cancer is really not one disease. Cancer is many diseases. I mean, there's lung cancer, there's prostate cancer, there's brain cancer. These are all different diseases. Even within each disease, there's different stages of diseases. And so cancers are probably literally hundreds of diseases. And we've made a lot of good strides recently to kind of identify specific treatments for each one. And particularly in the chemotherapy side, there's lots of new techniques coming out, immunotherapies, some of these targeted therapies that are molecular therapies that target the actual genetics of the cancer. And this is all very, very good. And this is why there's many more treatment options. But unlike some of these new diseases, sometimes you hear about these, miracle cures with these miracle responses where you have a complete remission, and that happens. It doesn't happen very often, and that's because cancer is a very complicated disease. And often, even within a patient, you might have 1 or 2 cancers, and the drugs may be affecting one or the other. So radiation is very effective because it treats all cancers. And as we'll see, the problem is, not the way that the radiation acts on the cancer, but it's just more about how do we get the radiation to the right cancer. So there's lots of options, and what we'll talk about today is kind of the middle one. So we use a machine called a linear accelerator, which we can see here, and it's a big, complicated machine. But hopefully, after today, it won't be so big and so scary. Okay. So preparing a treatment it's not a simple process, and I've kind of outlined here kind of four major stages for it. So I'm going to look over here so I'm not looking too. And when I look away from the mic, I can hear my voice going down. So what we do when we prepare radiation treatment is there's kind of these stages. The first step always starts with some sort of an imaging study, so a CT scan of the patient. And what we want to do is we want to know within the patient where is the cancer, right? Because we're going to point radiation beams at it, and we need to point them in the right place. If we point them in the wrong place, then that's not helping anybody. And this is what leads to side effects, because the radiation affects all cells, the cancer cells, but also the healthy cells. So every patient gets a CT study, and it's a different study than an imaging study. So we know the patient has cancer, so we're not trying to diagnose a new disease. What we're trying to say is, okay, the patient has cancer. What we want to do is we want to draw where it is. We want to draw the areas that are involved with the cancer, so where there may be some spread of the disease, the lymph nodes, and so on. And then we want to involve this in our target areas. So once you've done that, then we send the images to what's called the treatment planning system. And then within that system, now we have to arrange our beams. We have to, what we want to do is we want to use all the possible angles that we can so that we can get the radiation beam going right at the tumor. If we want to accumulate dose at the tumor and minimize the dose elsewhere, because the radiation affects the whole body, not just the tumor. That's the problem. The good news about radiation is that it cures all cancers, but the bad news is that it also affects cells that we don't want to damage. So we want to minimize that. So we have a fairly complicated process of treatment planning. There's many techniques for different sites and so on. And then once we've done all that process, what we do now, we have a radiation dose distribution over here, like the third slide, and we really want to optimize that. So we have all the dose that are where the cancer is. So we see that in red over there. And if you look closely at the side and had a better image, you'd see a little red line around the red part. And so that's where the target volume is. We've defined that as where we believe there's cancer. And now we want to put a high dose there, which is the red part. But as you see, there's dose everywhere else as well. And that's unavoidable because of the nature of radiation. And so we want to optimize that. And once we've done that process, what we now we can bring the patient back. So the patient was there for the CT scan. We bring the patient back to the linear accelerator, and now we're going to deliver the treatment. but we don't just deliver it in one treatment. So like it's not like a surgery where you come in once, you have your surgery, you go away. We do this many times, and so we fractionate it. So it's kind of like taking, like, you know, you go to you get a prescription for some drug, and you might say they take this over, they take a pill in the morning, pill in the afternoon over 2 weeks. It's the same thing. We want to minimize it. We want to give a certain amount of dose per day so it's tolerated, but the total dose we need to kill the cancer is much higher than that. And so by doing it over many days, we can get the dose we need to kill the cancer cells. One of the problems with, we'll come back to later, with the servicing of the equipment is that if the machine breaks in between those days, it's not like you can just kind of say, okay, we'll just pause and we'll come back, you know, maybe a couple of days later. The cancer actually can react negatively, and it can also, the stoppage can make the cancer actually grow faster, which is a problem. So we don't want that. So once you start the treatment, you kind of have to deliver it in that time. If you don't, it can cause unwanted problems, and so that's not good. And the other thing about the treatment is that, you know, we want to make sure that the patient is set up the same way as when we do the imaging. So if your patient's like this, when you're imaging them, and then they're like that when we're treating them, that's not going to work. So we have the devices to mobilize the patient and do it. So it's a big process. The whole thing takes typically maybe like about a week in order to organize. If we're in a rush and there's an urgency, we can maybe do it in less than a day. But it's not a simple process. It takes some time. So the kind of the problem, and I think, you know, for this group here that we want to emphasize is that, you know, this process that works very well. This is, you know, we've been doing this for a long time. The techniques have evolved, but we're just not keeping up. So the number of cancer patients has been projecting to increase. It increases as, you know, as the world ages, the larger incidence. And so these are some figures for the whole world. 2020, about 19.3 million people were diagnosed with cancer. And this will go up to about over 28 million by 2040. So these are figures from, you know, World Cancer Agencies who project incidence. And so to treat these patients, we need the capacity to treat them. So we need more equipment, more machines, more everything. And in 2015, there are about 15,000 linear accelerators in the world, and we'll talk about this a little later. And there are people who have studied this, and they said, well, in order to meet the need for treating all these people, we're going to need, by 2035, we're going to need about 24,000 linear accelerators. And then last, so I counted, and last year we're still at 17,000. So that's not going to work. We're not keeping up with demand. I mean, part of the problem is the equipment is, as we'll discuss shortly, it's big and complicated. So that's a problem. That really shouldn't be a barrier. We should be able to meet demand. And, you know, the people, you guys are a big part of the solution, and that's part of what we want to talk about today. And you know, lastly, there's a shortage of skilled people. So there's, you know, some medical physicists like myself who are needed to kind of, you know, look after the equipment and make sure it's calibrated correctly. The radiation therapists who deliver the treatment, but also I think more critically, the service engineers, the service technicians is really in short demand, and we need more people. Okay, so next one. So a little bit about the technology now. So linear accelerator is, you know, it makes an X-ray beam, you know, kind of like a diagnostic you know, device. But it's really different in that the X-rays are really the only similarity. They're really quite different. And so the amount of dose that we want to deliver for patients are measured in grays. So we typically, most cancers will get tens of grays, you know, maybe up to 50, 60, 70 gray in some cases. And that's quite different from a diagnostic X-ray machine. So I'm just showing a simple one here, but the same thing would apply to CT or to other imaging modalities. So in a therapy tube, we want to give a lot of dose because we want to kill the cancer cells. So the quantity is important. In an imaging study, you want to give a small dose as possible while still getting a good quality image, right? So in that case, dose is your enemy. The image quality is what you're aiming for, and you want to optimize the two. So you're looking at micrograys. So you're looking at a much lower dose. In radiotherapy, dose is our friend. Dose is what we want to deliver, but our enemy is, we know where we put it. We have to put it in the right place. So the energy is about, you know, maybe about 60. So the dose is about maybe 1 million times more dose. So 1 million. That's a big number. And then the energy is also different. So in radiotherapy, what we want to do, as I've shown here on the top of the graph, we want the dose to be kind of like, usually tumors are inside your body, right? So like I'm about maybe a foot more, maybe 16 inches wide. And so if I have a tumor in the middle of me, we want the radiation beam to get into the middle, and we want more. I want more dose there than I want on the outside, right? Because I want to minimize the dose to where I don't have a cancer. And so to get the dose there, we need a high energy. That's just the way how the physics of the radiation beam works. And so the doses, the energies rather that we're looking at are around. Typically, we use about a 6 MV beam. So 6 MV is kind of a short form for megavoltage. So 6 million volts. Whereas in a typical diagnostic tube, we're looking at maybe 100 kV. I mean, it varies depending on what we're imaging, but 100 kV or so. So we're looking at around a factor of 60 times a higher energy. So that's quite a bit. This is one of the reasons why, linear accelerators were kind of slow to develop, was to get that energy high was difficult traditionally, and I'll talk a little bit more about what that is. But same very similar. They both need radiation safety shielding. They both need similar things like that. But the numbers are quite a bit different. How do we do that? So how do we get that high of an energy beam? So, and this was a real problem. So when X-rays were first invented back, like in Röntgen, 1895, they started being used, very quickly for both imaging and for both radiotherapy. Like the imaging started like that famous picture of Röntgen's wife with the ring and the hand, and that was like instantaneous. Within about 3 or 4 months, with the first radiotherapy treatments, there was a doctor in Chicago who treated breast cancer with X-ray tubes. And so, almost right away, they realized we need a higher energy. It's not going to work with the same energies. And so there was a kind of this progression of the technology. And to use like the same, so in an X-ray tube, we have like a rotating anode kind of direct acceleration tube. You can get 100 kV. That's not difficult with kind of the transformers we have today. And you can just in a single transformer device, you can probably get to about say 500 kV pretty easily without things getting too big and too complicated. But that's about as high as you can go. And then people have tried. There was in the 1930s, GE came up with a tube that had a 1 MeV potential on it, and it was just a big, massive thing. And so the problem is these machines, not only do they have to get that energy, but it has to fit in a hospital room, right? So the intended location is a hospital. It's not a research facility. It's not somewhere where you have a lot of space. So it's got to fit in rooms that are smaller, much smaller than the room that we're in right now. So it's got to be small. So what we do, rather than using a direct acceleration like a traditional X-ray tube, is we use what's called the linear accelerator. So that's the device on the right here. So what we have is a number of cavities. So these are these cavities over here. And what we do is we feed microwave power, so RF power, and these go into the accelerator, and the microwaves kind of populate all the cavities. And then in each cavity will generate potential, like a voltage that's pointing in the right direction. And the way that the way it's organized, and the way the timing of the microwave, how it fills the waveguide, and how that potential kind of flips. If we introduce electrons over here, as the electrons go through each cavity, they'll get accelerated to a higher energy. And the energy that we'll get to will depend on the number of cavities we have. So all we need, if you want a higher energy, you just add more cavities. And we make these the waveguides made out of copper. They're very beautiful. They're very copper, when it's all polished and shiny, it's beautiful to see. It's like it kind of like, it looks white almost. It doesn't look like traditional copper looks like. And the way that the microwaves resonate, it's all timed, and you don't need any electronics. You don't need anything. It just all happens normally by the normal oscillations of the microwaves. And then the electrons will get accelerated, and all you need is enough RF power and the right number of electrons, and then we can get high energies and high doses. And so that's kind of at a high level how they work. And it's quite different than the tube, but in many ways it's much simpler. Once we built it, it's like the laws of physics take over and it works. So it's actually not that hard. But that's the kind of the simple part. But the complicated part is, how do we put it all together now so that we have a machine that works? And so you need other things, unfortunately. So it's not just the accelerating waveguide. You need a whole system around that. So we have to make the microwaves. So that's the stuff over on the left. Then we have to have an electron source or an ion source. So that's a little bit over there. That's on the left of the waveguide. And then once we've made this electron beam to a high energy, now we have to convert that to a photon beam. So we use the same method as we do in a tube. We strike a target. But now this photon beam has to then get pointed at the patient. It has to have the right shape. It has to have all sorts of things we have to do to that. So there's quite a few devices kind of go into the machine to make the beam. So on the left over here, we have the RF source. So the device down over here, this is called the klystron over here. So klystron is a big amplifier of microwaves. And so you feed in a low power microwave source and you amplify that. Then those microwaves go out into this waveguide, which is going to the accelerator until it travels along, because that's going to be far away. The klystron needs a high voltage pulse to it. So about maybe 100 kV, 100 kilovolts. So it's a lot of high voltage. Once the microwaves get into the accelerator, then we have we have an ion source for the electrons. And then once we get out, usually the waveguide, because it's longer, we want higher energy. It's pointing horizontally. So the patient is going to be down over here. Accelerator is going to be over here. So we got to get the beam pointed at the patient. So we need what's called a beam optic system. So we have a bending magnet where we redirect the beam now towards the patient, and then we have to make that beam into a beam which is useful. So now we have the raw X-ray beam. The intensity is varying. It's a good beam, but we need to kind of shape it so that it's useful for the patient. So we have filtering, and then we have collimation to make it the right size and so on. And this all kind of goes down in the area closer to the patient head. So there's a lot of parts. It seems complicated, but if each one by themselves and kind of in a linear fashion, it's not that difficult. That's the main way of doing that. So there's two kind of main manufacturers of these machines. So there's Elekta, and then there's Varian. So the Varian machine is the one on the right, on the left over there. So that's one I described before. It uses to make the microwaves. It uses a device called the klystron. So klystron, as I said, it's an amplifier of microwaves, and so it amplifies a source of say a few watts up to megawatts. It needs a high voltage pulse, about 100 kilovolts, so like a lot of high voltage. And the high voltage pulse is using some sort of a pulse transformer tank, so it's got it's high voltage. It causes problems. Things get big. That we want, and as I showed before, these machines have to rotate around the patient, so there's a rotary joint in between. So the Varian machine, there's a stand at the back. There's a rotary joint in the middle. The machine rotates around that joint, and then we have the beam delivery system, which I showed before. We have the accelerator, the bending magnet, and the dose collimation. The Elekta machine, it's similar but different. I mean, the two manufacturers, they're kind of like Fords and Chevys. They both make radiation beams, but they work slightly differently. They have transmission's not quite the same. So, or in this case, the waveguides are a little bit different. One uses the Elekta uses a longer waveguide because it's called a traveling wave accelerator as opposed to a standing wave. Slight differences. The Elekta machine uses the magnetron, which is an oscillator. So magnetron. Everyone here who has a microwave oven at home in their kitchen owns a magnetron, but the magnetrons that we use in linear accelerators they're more powerful. They make higher wattage microwaves, and so it uses a magnetron, and it uses a slightly different. So the accelerator is kind of at an angle, and it uses a slightly different configuration, but they're really essentially the same thing. So they work slightly differently. And then, for modern radiotherapy, this technique has evolved. And so when I first started in this business, the beams were all square, and then we had to add blocks in them to shape them. So because tumors they're not square. They have all sorts of shapes. And when we make the radiation beam, we want to shape it so it fits the tumor size. So when I started, we would have these blocks, these made out of cerebend, which is it's like a lead-like material that we put in the beam. Now we have what are called multi-leaf collimators, which you see on the left, and so we have these. The collimation device has these little leaves that are made, and you can shape them to pretty much any shape you like. And what we do with that is, as the machine rotates around the patient, we actually change the shape dynamically so that it's continually changing, so that we're optimizing the beam so that we can deliver the right radiation to the tumor and minimize what's going to the other areas of the machine. Most machines will have about 120 of these little leaves that are moving around. These are parts that often fail that need to be replaced because, as you can imagine, it's just the leaves are about maybe less than a millimeter wide, and there's 120 of them, and they're kind of traveling. And so, like anything, moving parts, things break, and that's a common thing that happens. It's not a complicated fix, but it's something that needs to be done. Otherwise, the patients can't get treated. Then, and again, to make sure that the patient is in the right place and that we're pointing the beam in the right place, we have to have the right kind of setup. And so we have a lot of immobilization. devices. So we want to make sure that when the patient comes back a few weeks after their initial imaging study, we put them in the same way as before, so that they haven't moved, so the beams will work. We have a treatment couch, which has to then it will has to elevate the patient to the right distance. It also will position the patient the right way. It rotates as well. If you see down over here, there's a rotating plate, so we rotate it that way as well. So we really want to use geometry to our advantage to have the beams come in from exactly the right angles in order to get the right dose distribution. And then we also have, on top of all this, we have imaging devices. We have a KV imaging device on the linear accelerator to do like a cone beam CT. So before we treat the patient, we can do a cone beam CT and then compare that to the CT that we did at the planning, and then say, okay, the patient's here, here's where we want them to be, and then we can automatically move that and then position the patient correctly. And so then we know that the patient's in the right place. And it's for advances like this that we've really been able to get more dose and really increase the amount of dose to the patient without giving too much dose to the normal tissues, to the healthy tissues. And so back in the 1990s, the early 2000s, kind of when I started in the industry, the questions were, well, how much dose do we need to treat a prostate cancer? How much dose do we need to treat a brain cancer? Or how much dose do we need to treat a lung cancer? And the technology evolved so that we could get the dose higher and higher and higher in a safe way. Today, as things are changing, the dose, really the questions are more around, well, do we need to give this much dose to how much to this area, and can we still get the same outcome? So it's more, we're kind of getting to the point now where we're kind of optimizing it, and we're kind of coming down in terms of, well, now we know how much dose we need. What we need to know is what else, can we get away with not irradiating these things over here, like these lymph nodes or these things. And so we're really kind of, it's coming around. The treatments are a lot less, the morbidity is lower than it was before, and we're getting the same cures. And then in combination with some of the chemos that are coming out, so what's happening with some of the new immunotherapy treatments is that the immunotherapies are working well, but they don't always work perfectly. So we're getting a lot of patients that come back that are now they're in survivorship. They've had a good response, but they still have these little tumors that we need to treat kind of elsewhere. So we need to treat small diseases. So the field sizes are getting much smaller. And so like again, when I started, we'd have these big beams for treating all these big areas. Now we have a lot of really small beams that are maybe like that big, and we're treating very specific areas. And so we need precision treatment to do this, and that's why we have that. So that's kind of an overview of the equipment, how it works. Any questions? I mean, I kind of went through like a lot in just a short while. So kind of like what type of cancer we have and the equipment we use for it. But any questions before we kind of go to the next, the next part of the presentation around the equipment and how it works?
Is there any like other significant differences between like the variant and the electro ones?
Yeah, so I mean the differences are, like the type of they use a different. One uses the klystron, one uses the magnetron. The accelerator itself is the layout is quite different. Like one's longer than the other, so they're kind of arranged differently. But maybe go back to that slide. From a servicing, or one forward, one of the differences is that I didn't emphasize this, but there's the electric machine. They like to divide the rooms. So this part of here is kind of in the back room. So this is not part of the treatment room. This is the treatment room, whereas in the Varian machine, the whole thing is kind of sitting in the treatment room. So the Electra kind of uses that to kind of like hide the kind of the stuff behind the machine. They use their imaging devices are like to do the cone beams. They're a little bit different. Electra was the one who started that. So they had their systems initially they had better software for it, and which worked better. But no, those are more or less even now. Maybe.
Which one? One has traveling wave.
Yes. Traveling wave. So traveling wave accelerator is less efficient in how it converts the microwaves to a high voltage, and so that's the Electra machine. Whereas the Varian machine uses the standing wave accelerator, so it's more efficient, and so that's why the waveguides are shorter, and so yeah. And the way that the Electra machine is lowered, this line over here is kind of what we call isocentric. So that's the line that the machine is rotating over, and it's lower than the Varian machine. And so if you're the people who treat the patients, the radiation therapists, are often female, and they're not to get into, but they're often female. They're often shorter, and so lower is better than. It's even me. I'm not tall. It's put this high. So when I'm setting up equipment, I'm always on my shoulders looking at things. And so the shorter it is, the better it is for that. So that's one of the differences as well. Yeah.
It's shorter in that area.
Yes. Yeah. Yes. Yeah. 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 Sure.
So, since we're much higher KPP, the target is.
Yes. It's very different from like a tube target. Absolutely, yes, it's very different. If you come down to our booth, we have actually one that we can show you. So it's a water cooled target, and it'll be made out of like a you know both tungsten is your typical material for targets because it's a high Z target. Often it'll have two materials. It'll have copper in there as well to kind of do some filtration, so we get kind of the right kind of mean energy out of it. But the main difference is that because the amount of power that goes into it, it's quite high. And if we didn't have good water cooling around it, it would fail almost instantaneously. It would melt. The target yeah, I mean, that would not be a good thing. So so it's smaller, and it's not, and depending on some machines will have different targets for different energies. So we'll have maybe more than one. Yeah.
Yes, sir.
So is the ion, one of the other pictures you were showing showed the R source, and then there was like the ion source.
Yes.
on that drawing.
Yes.
What is the-
That's the electron beam. So we can
there's
yeah. So
separate components?
yeah, that's just a fancy word for electron gun. So the ions we use are electrons, and so it uses just a hot filament that you make very hot, and then it emits electrons, and then it'll have its own little mini kind of little acceleration stage in it to kind of get the electrons away from the actual filament and then into the accelerator. And so yeah, it's an electron source, yeah. Just like in an X-ray tube. It can be. They used to be in some of the older machines. They used to be in different parts. It can be. It's not ideal, but the closer the better. But in today's machines, they're all integrated together. I think the last machine that I knew that had been different. I mean, the Siemens machine had them in. You could have them in a different room. Some of the older machines back in the 80s and 70s, they were quite a bit larger. But today's machines are all kind of integrated together. Is that about right?
Medical accelerators, great question.
Yeah.
Medical accelerators we're speaking about today, obviously very common. But if you're working in a research laboratory, where they'll have obviously very large type of accelerators used for research and development or different experimentations that are going on, very common to have some of these components we're speaking about, like the RF source.
Something on the floor below.
Yeah.
Do you
Yeah.
recall what manufacturer, model, effect, equipment, or how long ago it may be? Sure. Yeah, no, very good.
Yeah.
Good question.
Yeah. You get a question? Well, the way I did it is maybe not the way it should be done. My career is kind of weird. So I started off as a service engineer. I worked for a company. We had a contract with Siemens back in the 1990s, and then I retrained as a medical physicist. And don't do that. I ended up going to school a lot longer than I needed to, and I spent a lot of time doing that. But so is it around being a service tech, like a service engineer, as you're asking, or a medical physicist? Medical physicist. So usually there's two kind of entry paths. You need about a master's degree in a medical physics area, and then you need certification from the American Board of Radiology. And there are training programs for that. They last about 2 years. In the U.S., about 2/3 of medical physicists have master's degrees, and then about 1/3 have PhDs. The PhD people tend to work in the more academic centers and some of the larger centers, and that's, you may add on another 5 years for that. It depends on what your goals are and what's right for you. But yeah, it's comparable to the amount of time to be a medical doctor. Yeah.
But your career path is a unique one, really.
Yeah.
Right? Servicing the systems, working from that end, very important. And then taking that and the career ladder, going into the medical physics stream.
Yeah. One of the things I've tried to explain to a lot of my colleagues is a lot of the machines are kind of viewed as a black box, which is really something that I don't see as benefiting anybody. If you, in order to understand how to optimize the machine for patient use, it's really helpful to know a little bit about how the beam's configured, how everything works together, and it's really not that difficult. And around servicing the equipment, I mean, this industry is very cautious, because we're using radiation. Radiation is, it's as a medicine, it's a great medicine for cancer, but radiation's hazardous. You can exposures can have health consequences. And the machines are big, and the machines are, and any kind of chance of breaking it is people are worried about that. But most importantly, you can't undo a radiation. So once we treat a patient, if you make a mistake, you can't press delete and go back. Like that's there. And so we continually check for mistakes. And so one of the reasons why it takes that long to prepare treatment is because we're looking for errors all the time, and which is good. We have a very, very good safety record in radiotherapy. The number of mistakes is very, very small. I mean, there are some, but it's very small. And the ones that occur are generally not very, they're not serious. But having said that, with the world, with more incidents of cancer, we really need to, kind of rethink that. I believe we need to kind of rethink how we do this, so that we want to do the right amount of checking, but no more, and certainly no less. And so what is that right amount? And so with my background, I do try to, sometimes I get into trouble because I say, do we need to do that? And then people say yes, and then I kind of say, well, are you sure? And then that kind of leads. But I would encourage people to kind of, I think if you're interested in this area, is to try to help with the problem of, we want to make it safe, but we also want to make it more available to as many patients.
So historically, we want to talk a little bit about, how has service and maintenance of these type of technologies been carried out. We look back over the last 30 to 50 years. I go back to that. I was almost 40 of it, so I've witnessed a lot of this as it went on through the decades. But historically, again, it was very much an outsourced service, outsourced to manufacturers. And then as time went on through the later decades of the 20th century, independent service organizations come into play. But in that same period as well, in-house engineering groups, having individuals that provide services locally began to expand as well and need there. So has that changed much today? No, not really, but the need for, again, individuals in any of those three sectors is still an increasing need with a low supply to meet. And, what also has changed, though, as we look back, so 30, 40 years ago, today, the complexity of equipment as well has also changed with all of the technological areas of IT interfacing and computerization into the systems, basically going from analog type equipment to more conventional higher end technology today. Those are also been factors that are strong too. What has been kind of also been traditional, let's say, over these last 40, 50 years is because of the type of patient, the type of activities involved with patients, and as Marco touched on, treatments of cancer are so paramount to occur as planned, designed, and delivered. The cancerous tumor does not stop growing at any point in time. So the ability to assure that patient's care is carried out as the treatment plan has been designed is really, really ultra critical. And so the ability of staff to be able to be a part of that team, and I'm going to speak a little bit here around the service team, because again, HTM professionals here in our room today do take in a lot of this, is that the need for competent and the need for individuals that can triage, critically think through situational awareness of an equipment situation, that bring resolution is so important to that patient or that patient's family involved in their care of patient or in the care of the cancer treatment. So we're going to talk about in this last half there a little bit about what the current state is today in the industry and what we see going forward in the future. And again, where the opportunities are for the HTM professional to help support not only their organizational that may be today or the future organizations that they serve, but also kind of explore a little further about the career ladder opportunity for individuals that may want to expand or channel more into some of these areas of radiation oncology. We hear a lot today about self-performing of services. Has anybody in the room here not heard that term, maybe in their organizations or just in the industry, right? That seems to be, a buzzword, right? It's not new. The whole idea of self-performing has been around for a long time, many decades. But more now than ever, the self-performing model in healthcare technology management, HTM, really is a driving force. We know we have a healthcare system here in the United States that almost all healthcare organizations are impacted by reimbursement changes that continue to not only kind of trend downward, but in many cases, insurance abilities for individuals as well is also challenging for folks. And so these hospital and healthcare organizations are looking and need abilities for staffing to be a resource internally, to be a resource even from an outsource perspective. We see as well the vendor environment. In this case here, we spoke about two major vendors. There's a few others too that are coming into the market. Their need for future engineers, future technicians, and what does that, how do those applicants get developed? How do those folks get identified? So we want to talk a little bit about here in this slide here, and we're talking about a hybrid model here. I think that's very common in our HTM world. High-end advanced equipment is hybrid models. It's kind of a mixture of in-house, mixture of outsourcing, either through an OEM or through a third-party organization, and perhaps how do they all blend together? Right? How do you feed that together and into a self-performing model? Why is that important? Why is that important? And also, too, why is it important for HTM professionals to really start to explore further either the technician or even leadership teams or even students looking for their career ladder? Why is it important that HTM get involved? We kind of touched on earlier, staffing shortages. That is continuing to be developed in all areas. And equipment owners too, we're seeing this trend across the country. It's not a trend that we haven't seen before, but we're seeing it again, where equipment owners are beginning to clearly lean more to being internalized versus outsourcing supplies. Well, we're looking for hybrid models to support mechanisms as well as support internal tools. So there's a lot of dynamics to that. And what does that power bring? From an equipment owner perspective, the ownership, stewardship, accountability to the team of patients. That is a lot of what these professionals that go into these areas here will need to be focused to and be driven towards as well. So summary, and we're kind of moving towards, here we're a little bit of a wrap up, but and then we'll have an exam at the end for today's entire session.
That's right.
We'll get those handed out to you here shortly, but want to kind of talk a little bit about, as Marco went through the beginning objectives. And so how do we address the objectives? So we hopefully believe that you will feel the same way. We want to introduce radiation oncology to the HTM professional. Slides 4 and 7, we spoke around. We spoke around physics. We spoke around the functionality of the systems. We spoke around the 2 differences or 3 differences or more of manufacturer types out there. So hopefully we've given you today at least a very novice entry level thought approach to that and take a look at that. Overview of the industry. Hopefully again today we've given you some of that. We talked about that from slides 8 through 12. We want to again get a message out to the folks that have attended here today. This is one of the areas, I can't think of others per se in healthcare settings that are looked at in such a high regard. The treatment of cancer patients, the equipment that's related to treatment of cancer patients in almost every healthcare setting is probably almost at the highest level of regard through their leadership teams and other clinician leadership groups as to how important that area is. We want to kind of, demystify that a little bit, kind of share to yourselves here as HTM professionals that, it is an area, yeah. But going into it with the right approach, the right type of passion and philosophies to it can be a difference maker to the patients that are served and the patient families as well that are part of that treatment process. And then lastly, we talked a little bit about how they were serviced traditionally. All three of those models work very well. We want to say that. The manufacturer service direct, third party, in-house, all very well work, all very well functional. It depends on an organization, size, resources to it. But from a hybrid modeling, probably could be the most powerful way to approach it, as you look at servicing as well. So those were kind of our summaries from today's objectives. We've got a few minutes left. So we want to give everybody some time to ask a few questions, and of course, give them a little bit of time before we go to the exhibit hall and lunch. And we know that we're your barrier in between lunch. So I just want to open the floor up. Do we have any kind of wrap-up questions for Mark or myself that we can maybe speak to here for you?
Yes, another question, I guess for Marco. Is there anything special you have to take into consideration when installing linear accelerators? So like the
Oh, yeah.
installation process?
Oh yeah, actually Al could probably speak that better than I could. I'll start, but I'll pass it off to Al. I mean, the installation process is, first the machines, these are heavy machines. These are like 15,000 pounds. They have to be rigged in. The positioning of them is very important. Because in order to define that rotation point, which you call isocenter, we have lasers on the walls, we have camera systems, and they all have to be pointed to the right place. And so that has to be positioned very well. It starts off with a base frame that you have to put into the floor, which has to support it, all that weight, and then that also helps with the positioning. And then as you go through getting the machine working, you're turning it on. It's about today it's probably about maybe a 2-week process for the manufacturer to come in and just get all the systems going, kind of one by one. And then we go through a calibration process at the end to make sure that the beam that it makes is what we understand, and then we model that in our treatment planning systems so that we can plan patients with it. And so what matters is the beam model in the treatment planning system, does it actually reflect what the machine is actually doing? So that process of validating that as well. So the whole process is about maybe a 4-week process, and there's a number of steps in there that are pretty important, yeah. So,
yeah, that's a great question. That is the installation of the Linax itself, but leading up to that, the design, the construction, and all of that component, the building of all, because the suite that's going to house this Linax is much different. Obviously, as we know, that a diagnostic suite it's going to be built with high density concrete. Wall thickness is probably anywhere from 2 to 4 feet. There was steel involved, steel or lead brick shielding involved as well. So the construction component alone itself could be a 8 to 9 month project.
Right.
The space that's going to occupy is that. But the involvement of the HTM engineer really there is still, again, programmatic planning and development, even project management are key subject matter experts within an organization to assist with these types of projects. So again, there's a very holistic approach to this. Servicing is one piece. There's a lot of other programmatic planning that the HTM engineer can involved too as well. So great question.
Yeah, good question.
Others? Yes, sir. Mark over that.
How someone go about getting a service technician position for accelerator?
Manufacturer or in the hospital or yeah, that's a very good question. Actually, I think Al's probably better suited to answer than I am.
That's
Yeah.
not my role. That's a great question. And I'll give a very neutral answer to you.
Right.
Oh, yeah, that's a great idea. So the question, thank you. The question was, how does one enter into becoming a service engineer, explore to be a service engineer for Linux salaries?
Right. Yeah.
Very well.
Technician. Yeah.
So I think there's a couple pathways and channels. Historically in this industry, many people have come into the Linux service world, many times coming from the military because of their involvement with radar or other type systems. But the HTM engineer, obviously, some of the schoolings that are now have been out there do teach and do touch into it. CDET now has a program that is a 5-tier program that also is totally focused at that. So it's a great preparatory way to enter for that as well too. And again, I think also the last thing I would add to that is, again, research of one, obviously through their peer groups, through their HTM associations, others as well too, to identify career value opportunities. That's a great question as well. Others? Yes, sir.
Like two, but one would be Marco. How, you said there's 7 to 8 weeks. How long is each individual treatment?
So each treatment is usually done in about a 15-minute time slot, and the actual radiation on time is maybe a couple minutes. Depends on. Sometimes it can be longer. And during that 15 minutes, the patient will we'll go get them in the waiting area. Some patients are not very mobile. Some patients are mobile, and so depending on that, so we have to they come in, and then we set them up to get them in the right position. And then but the beam on time is that's beam on, the machine rotates around, then beam off. That's not the longest part. It's really the patient positioning, bringing the patient in the room, and then getting them out of the room afterwards as well. Because often the patients are these are cancer patients, so they're ill, right? So yeah.